talk about the network. Start with. So capsule definition. Okay, so a blockchain is a set of data plus a contract of some sort plus immutability. So immutability I'll talk about, but it means when you put something in, you can't change it. And various kinds of encryption. And there are a variety of different encryption strategies. And the platform for a blockchain is distributed. And the reason for the distribution is to give you high availability. And there's a consensus mechanism that's part of the platform. So I will mention Bitcoin. So the Bitcoin consensus mechanism is essentially based on voting. There are other consensus mechanisms as well, which I'll talk about. Okay, so that's the capsule introduction. You now know what blockchains are. You can leave. Yeah, it looks awkward if you leave in 2 minutes. So hold off for a couple minutes before you leave. Okay, so let's take a public blockchain network. So as you can gather from the title, blockchain networks can be public or private. We'll start with the public one. So there's a protocol for replication. I use the gossip protocol typically. Every node has a replica of the entire blockchain. That gets you availability. Right? You have replicated in a distributed network, and it makes it efficient to read. So you would read from a local node or a close node. The node content is a sequence of blocks with transactions in them. And a transaction isn't accepted until consensus is reached, whatever consensus mechanism you're using. And each node has a set of outstanding transactions. These are the node's proposals for the next transaction. And they may or may not be accepted. So again, that depends on some of the variants I'm going to talk about. So Bitcoin has a platform. Ethereum has a platform. IBM is promoting something called Hyperledger Fabric. So Hyperledger is what's the word I want? It's kind of an Apache-like foundation, and it has a variety of different tools in it. And one of the tools is Fabric. So that's why it's Hyperledger Fabric. There are other platforms. I mean, Amazon has a blockchain platform. Google has a blockchain, I can't say it, has a blockchain platform. Doesn't roll off the tongue. So there are multiple others, but those are your, at one point, so I am a client for a MSE team, a Masters of Software Engineering team at Carnegie Mellon. And they're working on a blockchain project, and they were asking what platform should they use. So I brought up an old joke. So I don't know how many of you are old enough. But IBM used to be the primary manufacturer of hardware. And so there was a joke going around that you never got fired by buying IBM. If you were not, so the old people are nodding. Yeah, for your youngins, that's okay. So my comment was, you won't get fired if you use Ethereum, because that's kind of the equivalent these days. So Bitcoin is really pretty simple in blockchain terms. It has one use, which is Bitcoin currency, and that's not totally true. They're sort of expanding it a little bit, but in general, that's pretty close to true. Ethereum has a Turing-complete programming language, so you can make Ethereum do whatever you want. And again, if you're old enough, you've programmed in Turing machines, and you know that's not an easy thing to do. So it may not be easy to make Ethereum do what you want, but you can. And you write a smart contract, what's called a smart contract in this language, that says essentially what a contract is. And I'll talk about that. And there are other rules. So there are rules that govern costs and fees. And one of the things about the public network is what motivates you to want to be part of the network, what motivates you to want to host a node, and so on. And that has to do with the fees that you receive for doing that. Hyperledger Fabric is an IBM product initially. Get Kurt to talk about open source and where it comes from and who supports it. Contracts are written in a programming language called chain code, which is actually then translated into a programming language called Go. Okay. So there are lots of languages. Or you could write it in Node.js. And the intention is to allow other programming languages. It's also Turing complete. And there are plugins that exist for some of the variants that I'll talk about in terms of contracts and consensus mechanisms. So what are some of these variants? Well, the first and most important is the trust model, the consensus model. And then you can put data on you can have data on the chain or off the chain. So data on the chain is guaranteed to be immutable. If you don't know what that means, it means you can't ever change it. Data off the chain, you have to take special mechanisms to ensure that it's not modified when it's off the chain. Another variant is whether it's a public network or a private network. How much can you customize it? The various fees and networking. What's the incentive model for encouraging people to be part of your network? And is this a permission or a permissionless kind of network? Can anybody join, or do you have to be a member of the in-club? And I'm just going to introduce it now, and some of these ideas will show up later. So there questions? Yeah, I like questions. So so there are two basic consensus models. One is distributed consensus. At each round, so I said that nodes have unauthorized transactions. So what you do is you propose your transactions, and you broadcast that block, and other people look at the transaction and say, this is in fact a valid transaction, we will accept it. If there's a sufficient number of those, then it gets to be an authorized transaction. Okay. And sufficient number, there are a couple different models for that. At this point, we'll just say it's a consensus kind of operation without going into the details. There's proof of work and proof of stake and so on. And then other nodes are going to accept or reject this block. And they can extend the blockchain. I accept a block as an entry in the blockchain. I accept it. Or I want to accept one that came in earlier. So you have competing nodes proposing transactions. You may have two competing nodes that propose transactions at the same time, and there's a mechanism for time-stamping them and ordering them. And if a node doesn't like one transaction, it can accept an earlier one. Again, there are rules that govern these kinds of things. So all the users have a copy of the blockchain. Any user can propose a new transactions. If you are in the cryptocurrency world, then new transactions are difficult to do computationally. So I'll talk about hashing in a minute and what you hash, but difficult to do computationally means that your hash has to start with some fairly large number of zeros. I don't remember what the magic number is. Let's say 20 zeros. And if you know anything about hashing, it's a one-way mechanism. You can't unhash. And so the only way to satisfy that is through trial and error. And so that's what somebody asked me earlier, what mining was. And so people are off trying to generate new transactions by doing what's called mining. But the transactions are easy to verify. And we'll see this when we get to cryptography. Things are difficult to generate, but easy to verify. And so any node can look at a transaction and say, this is a valid transaction. So they'll take the hash, they'll count the number of leading zeros, and lo and behold, it's valid or not. And different consensus models for Bitcoin and Ethereum are your vote is weighted by the number of cryptocurrency things you have, the number of bitcoins you have. In Ethereum, they're called gas, so the amount of gas you have, which doesn't seem quite the right model. Well, it depends what you mean by gas. So there's gas in a car, and there's gas in your stomach, so it kind of depends. But it's called gas. And so there's proof of stake, which is how many do you have, and there's proof of work, which means, I've spent a lot of time doing this, and I'm entitled to some sort of reward, more or less. And then the other consensus model is super user. We have special people, and these people are authorized to accept transactions. Okay, so if you go back to the history in Bitcoin, one of the arguments for Bitcoin is the libertarian argument that we don't trust no stinking government. And so we don't want any super users. We want the community to decide what to do. And that's the proof of consensus and so on. If you apply blockchains to a commercial environment, you're a bank transferring money overseas to another bank, you don't want the community to decide, is this a valid transaction or not? You want somebody that's authorized to do that. So super users are common in the I want to say industrial. That's the wrong word. In the environment where you have industries, can't think of the word. And there are rules. Just like super users on computer systems, you may have to take two. There are a number of rules that prevent super users from going rogue. Okay, so that's one variant. Okay. Second variant is are things on the chain or off the chain? So things on the chain are guaranteed to not change over time, but the chain may get very big. So this MSE project I was talking about, they're looking at audio transcripts and audio recordings. That's a lot of data. And so what you don't want necessarily to have every node have that. What you would like to do is be able to retrieve it and verify that it was in fact the node that was analyzed for one reason or another. And so you would put that data off chain, and that would improve the performance. But it calls into question the integrity of the data. So you have to do something to guarantee the integrity of the data. And that may be a hash of the data item. It may be something else. This data is off-chain, so I don't have the blockchain mechanism to guarantee integrity, and integrity checking is easily done with hashing. Okay, another variant is, are you going to have a public network, a private network, or some mixed bag? Anybody can log into a public network, so you can sit down at your computer and log into Ethereum. You can log into Bitcoin. You have to create an account, which gives you an identity. But once you've done that, they don't care who you are, and that's part of the charm of the cryptocurrency, is I don't care who you are. And more than that, it's hard to figure out who you are. But everybody can look and see what happens under your identity. Everything is public. Although when we get to encryption, that may not necessarily be true. Consortiums are cross-organizations. So enterprises, that's the word I was looking for before. So enterprises might be consortiums. And a private blockchain is within a single organization. Okay. And you can have private subsets of a public blockchain. So if you're using Ethereum, you can set up a private network on Ethereum where you have to log in, and only certain sets of users can do things, and you can have the consensus model that you wish. So you could have a super user consensus model on top of the Ethereum platform. Ethereum charges you fees, so you have to pay those fees in a variety of ways. But so you can have private public networks, I guess, private subset, virtual private networks. Okay, there we go. So there's even a modern term for that. Some blockchains are hard-coded. Bitcoin has a certain set of rules, a certain contract with the users. Can't change it. That's the way it is. If you write a smart contract, that lets you set up your own transaction rules. I'll get into more detail on contracts in a minute. So again, the Ethereum language. And they're called smart contracts. Yeah. What's the incentive structure? It has to do with if you're in the cryptocurrency world, then you can be incentivized by giving new currency. So if you create a new block in Bitcoin, you get a Bitcoin, or I don't know what fraction. You get some fraction of a Bitcoin. And the same in the other cryptocurrencies. If you just are copying things and you're not successful in creating new ones, there's also an incentive structure, fees that are paid. If you have a totally private network, then the host organization, whatever it is, will pay has to pay the computational cost, but there are no fees for using the network. Again, permission or not permission. Do you have to be part of, do you have to have permission to use this private blockchain? If you do, then there's an authorization mechanism, authentication mechanism rather, in order to get in. Or if it's public, you don't need permission at all. As I said, anybody can log into Bitcoin and start to play with it. And there are various kinds of permissions. There are permissions to initiate transactions. There are permissions to mine, to propose new things. There are permissions to create particular assets. Okay, again, this all depends on the details of the application that you're using blockchain for. So think of blockchain as kind of a database in a way. And so, what are you going to use the database for, and how are you going to allow access to it? Well, it depends on what you want. Depends on your application. I said that. Okay, so what are the pieces? So just to repeat, we talked about the variability. Let me talk about the data. So a blockchain is a linked list of blocks, and each block is a collection of transactions. Okay, so the reason the transactions are collected into blocks is for performance reasons. You're shipping this around the network. And you can call this a distributed ledger. Sometimes you'll see references to distributed ledger technology, DLTs. Okay, so first you think of it as a linked list where each block is linked to the prior block. Okay, so it's not a linked list where you start at the front and go to the back. It's a linked list where you start at the back and go to the front. So adding a new transaction depends on the consensus model. So what about the contract? So a contract is a specification of how individuals or entities can interact with the blockchain. So again, if you think about the financial world and about cryptocurrency, what's a transaction? Transaction is I want to transfer some money to Kurt. How do I do that? Well, I have to have an account. I have to have money in the account. I have to own the account. I have to know, not that Kurt owns the recipient account, but I have to know the identity of the recipient account. Okay, so if I have an account, if I have money and I know where it's going, I can transfer it. Okay. And so that's a specification of a particular action within the blockchain. Just spending money. The contracts can be explicit, meaning that they are done in this smart contract language, and we'll see how you can encode that in a very efficient way in a bit. Or they could be implicit. Okay, so Bitcoin has a bunch of rules. You live with their rules. And it can be hard-coded or programmable. Okay. And I talked about some languages for smart contracts. So the Bitcoin contract, you have accounts. You have, that's an individual, can have one or more accounts. You have spending, I can transfer money. You have mining, I can create new Bitcoins. And we have consensus validation. That's all built into the Bitcoin structure. But that's the contract. And the fees are part of the platform of using Bitcoin. So there are also fees associated with this that are, you can view as part of the contract, but they're really part of the contract associated with using the platform rather than using the network. Ethereum contract, if you're doing gas, if you're using Ethereum for cryptocurrency, then it's the same set of rules as with Bitcoin. If you're using it with your own smart contract, then it's whatever your contract says. So you set up your own rules, you write your program to manage that, and you have a contract. The Hyperledger contract is specified in chain code, which again is Go or at the moment. And it's designed for enterprises and it's a private platform. So one of the things that's happening commercially is that various players are vying for, supremacy in the blockchain world. Okay. So again, you have Google, you have Microsoft, you have Amazon, you have IBM. They're all saying, use me in the cryptocurrency world. I mean, in the blockchain world. So what about immutability? So it rests on two foundations. One is hash codes, and the other is the difficulty of modifying the blockchain. So again, we have this linked list of blocks. What's a hash function? So I'm hopeful everybody knows what a hash function is, but if you don't, so a hash function takes any string as an input, produces a fixed size output, and it's efficient to compute, and the chances of collisions are very, very small. The chances of two separate entities hashing to the same thing are very small. Okay, so SHA-3, for example, I think is the current NIST approved hash function. Now, how does this work with the linked list? On block 3, I will have a hash of block 2. On block 2, I will have a hash of block 1. On block 1, I have a hash of the origin. What does this mean? I can't change, if I change block 2, then its hash value changes, and I can recognize that by looking at block 3. Okay, so what this means is if I'm going to change block 2, I also have to change block 3. And, question? Or no? No. And so that's one of the bases of immutability, is that if I'm going to change anything in the block, I can recognize it by looking at my blockchain. Efficiently computable hashes are easy to compute. Okay, so what keeps me from changing the whole blockchain? Well, it depends on the trust model you have. If you have a consensus model, then it's difficult computationally to get valid blocks. So if I change something in block 2, it's difficult to show that in block 3. I have to, again, make sure that block 3 is a valid transaction. Okay, and since mining, they're doing that is computationally difficult, it'll take me a long time. There are a lot of computers. If I have a super user, then the super user has to approve the modification. So in the consensus model, any user can recognize a chain because I have this linked list of hashed blocks. The validation will depend on the consensus model. So again, proof of stake, proof of work. You know, if I have super users, then the super users have to approve the change. There's also something, an efficiency mechanism kicking around called a Merkle tree, which surprisingly enough is named after Mr. Merkle, probably Dr. Merkle. And that's a data structure that improves the performance of testing blocks. So it's actually quite a clever data structure. It's a binary tree where each level up is a hash of the children. And so if you're going to modify one, then you can detect that by looking at the parent. So it's not quite obvious here, but this one is a hash of L4. This one is a hash of here. And then this is a hash of these two guys. You know, so it's a binary tree. And it's strictly a performance thing. It doesn't affect the logic of it. So what about encryption? Okay, so encryption starts to get complicated. So we'll start by talking about NP complete. And then we'll move to what's called zero knowledge proofs. And then we'll talk about quadratic span programs. Okay, you don't really need to understand this. And I say that because I don't really understand it. At least your level of understanding has to be enough to give a talk at SATURN. How's that? And I use me as the example. So what's NP complete? An NP complete problem is one in which there is no polynomial solution, polynomial time. So polynomial in the length of the expression. So you have an expression, and the canonical NP expression is a Boolean expression, A and B, or B and C, and blah, blah, blah. And that is NP complete because it's very difficult computationally to find a solution, a set of zeros and ones that make the whole thing true. But it's very easy to verify that a set of zeros and ones, in fact, make the whole thing true. You can verify it in linear time. I'm just going to run across the string and calculate the zeros and ones and go up the tree. But generating it is very difficult. And so the Boolean satisfiability problem, which is I have this Boolean expression and I want to find something, a set of zeros and ones that satisfy it, is NP complete. And the theoretical thing is if you have a problem that you want to show as NP complete, what you do is you show how you can translate it into the Boolean satisfiability problem. That's kind of the basis of NP completeness. So again, finding a solution is computationally difficult. So NP complete is one of the open questions in theory of computer science is the set of NP stuff equal to the set of polynomial stuff? So the stuff that you can't find are there truly expressions for which you cannot find a polynomial-based solution? And that's been an open issue since the 70s. Steve Cook invented this whole thing. The conjecture is that they are different. Everybody is assuming they are different. And this is the basis of modern cryptography. So the Boolean satisfiability problem. Okay, so what's zero knowledge proof? So we'll start with something called the Diffie-Hellman algorithm, which some people think ought to be called the Diffie-Hellman-Merkle algorithm. And this dates from the 70s. And it's the basis of SSH. So the idea is that you are on an open network. You want to set up a secure communication. So you have Alice and Bob, who always seem to show up in security examples. And they want to set up a secure channel so they can communicate without the eavesdropper Eve listening in. So they do this using NP complete, but you know, I've always found that difficult A, to understand, and B, to explain. So I'll do it with colors. So Alice and Bob agree on a common color, which in this case is yellow. Alice chooses a secret color that she doesn't tell Bob. Bob chooses a secret color that he doesn't tell Alice. And they mix their two colors together. Now they share their mixtures. So Alice gets the common color plus Bob's secret color, and Bob gets the common color plus Alice's secret color, and they have done this over an open network. So Eve is looking at these transformations, but she can't decode the colors. Okay, so I'm looking at a mixture of yellow and blue, and I can't decode that into yellow and blue. Now Alice adds her secret color to Bob's mixture, and Bob adds his secret color to Alice's mixture, and now they each have a color which has three components: Alice's secret color, Bob's secret color, and the common color. This common color, and they both came up with the same answer because they have the same components. This common color now can be used as the secret. It's the shared secret between Alice and Bob, and they can use that to encode their transmissions. Because it's difficult for Eve to decode the colors scheme, or if you translate that into NP-complete, it's difficult to decode the numbers that get sent around. This is now secure for transmission, and this is used, so it's used in SSH, and it's used in TLS, and it's used to set up a secure communication channel, which might be used to do other things, set up them even more secure in a different way. Okay, so now we have zero knowledge proofs. Okay, so we kind of understand the Diffie-Hellman idea, is that I'm taking things, I'm putting them together, and I have an eavesdropper that's listening, but the eavesdropper can't figure out what I'm doing, what's going on. So the zero knowledge proof, Alice generates two keys, again using similar techniques, and one she keeps secret, and one she shares with Bob. Now Alice claims knowledge of a particular fact. Okay. And she encodes that knowledge using her secret key. And she shares the encoding with Bob. Bob doesn't know what her secret key is. But Bob uses the shared key. There's a relationship between the shared key and the secret key. Bob can use the secret key, or the shared key, to verify the truth of the fact. Okay, so Bob doesn't know what fact it is. Bob just can tell you whether it's true or false. So that's why it's called a zero knowledge proof. You can verify that Alice, in fact, knows something by using this shared secret, but you don't actually have any insight into what it is that Alice knows. And that's called zero knowledge proof. One of the things I learned by doing this is that there are very few people in the world that understand cryptography and can write English. Yeah, just a minute. And one of them's at Johns Hopkins, and his name's Matthew something or other. So he's a very clear writer, and he understands cryptography. Yeah, question?
Yes, thank you. So when Alice shares the secret with Bob, the first step, how does she share?
So using the Diffie-Hellman. So Diffie-Hellman gives you a way of sharing things.
So that algorithm, also the first step, they need to agree for the common color. How they agree for the common color?
Oh, they can do that in the open. So I agree on our common color is going to be, I propose that our common color is yellow. You say, okay.
So that can be done in an open environment?
That can be done open, and Eve knows what the common color is. Now I make up a secret color, which is blue, and you make up a secret color, which is red, let's just say. And I mix the blue and the yellow, and I get a mixture that Eve can't can't decompose. And you mix your red and the yellow and get a mixture that Eve can't decompose.
Yeah, I understand that part. It's just the first part, if they get the common color shared, talk openly, everybody can know that common color.
Yes.
Then if people can listen to their traffic, so other people can also use their common color to.
They can use the common color, but they don't know the secret color. And they can't decode the mixture. So you're not using the common color for communication. You're using the common color as a basis to come up with the shared secret.
Okay. Okay, I will try to understand. Thank
Okay.
you.
So zero knowledge proof is a technique for verifying that something is true without knowing what it is that you're verifying. So if you go back to a transaction in something like Bitcoin, I'm sending money to Kurt. People can verify that I have that amount of money without knowing how much money it is and how much money I'm sending to Kurt. That's the fact that is, I'm claiming I have that amount of money, and you can verify it with a zero knowledge proof without getting any insight into how much money it is. So that's the application of that. Okay, so again, back to the Diffie-Hellman, you have to factor large numbers based on large primes. So a large prime is, a 256-bit prime. Okay, so there's a good question. How do you generate a large prime? Anybody have any thoughts? Okay, so the first step is you generate a large random number. So how do you generate a large random number? This is something you should know. Okay, so it turns out you can't use a pseudo-random number generator because a pseudo-random number generator on your computer will generate the same number as it does on my computer, and we don't want that. So what we do is a trick like counting cosmic rays in a unit time. Okay, well, counting cosmic rays is a little bit difficult, and so there are tricks like analyzing the turbulence over a spinning disk. And if you look up I think it's X-random in Linux or Unix, they use tricks like that. Well, that was okay as long as you had spinning disks, but now you don't have spinning disks anymore, so how do you do it? And it's some sort of magical electromechanical kind of thing that you measure. And you can't even repeat it on your own computer, let alone on someone else repeating it, because the number of cosmic rays, I like the cosmic rays even though people don't do that, number of cosmic rays you're going to count in a unit time is going to vary depending on sunspots and all kinds of other things. Okay. So the tricky thing, or the interesting thing about zero knowledge proofs is that any NP complete problem, the Boolean satisfiability problem, or anything that equates to the Boolean satisfiability problem can be done using zero knowledge. You can turn that into a zero knowledge proof. And that gets us to quadratic span programs. So back when I got my PhD, it was in theory of computation, and I used to think that I understood theory of computation. These are the most complicated algorithms I've ever seen. So the generating a quadratic span program has like 12 steps. First step had like 13 little steps. And after 2 months, I was very close to understanding the first step. I didn't quite get there, but I was very close. So I mean, these are complicated algorithms, and the people that understand them have my greatest respect. Okay, so what happens? We have a contract. I'll talk about that in a minute. And I put it into a key generator, and out comes 2 tokens. There's the prover token, which is what Alice uses to say, I have complied with the contract. And there's the and Alice uses the prover token to come up with a compliance token. The compliance token is visible to everybody. So anybody can now verify that Alice has complied with the steps of the contract. That's kind of the big picture of quadratic span trees. All of this is public. The contract is, most of this is public. The contract is public. These tokens are public. This is public. There are some magic numbers, back to the secret colors. There are some magic numbers inside the key generator. And that's the only thing that's kept private. So if you have those magic numbers, you can decode everything. If you don't have those magic numbers, then you can't decode anything. Okay, so we have the provers and the verifier, and we generate that with the token. We have a contract. We express that contract as a Boolean expression. And we put that into the key generator. Okay, so again, any NP-complete problem can have a zero knowledge proof. That's what I'm generating here. And then I get these tokens, prover token, the prover key and the verifier key. Okay, so this is how the prover and the verifier work. So the prover can't cheat because the verifier token is public and anybody can verify whether or not Alice in fact knows that fact, whether Alice is adhering to the contract. The verifier can't cheat because all these things are public and anybody can verify whether an assertion is true. So how do quadratic span programs work? Any Boolean expression can generate a function that will determine whether or not the input satisfies that expression. Remember I said it was easy to verify whether a set of zeros and ones satisfied a Boolean expression? Okay, well, I'm encoding that into this function. Function works in linear time, length of the expression. And the function is only a verification function. It's not a satisfying function. So there's this distinction between satisfaction and verification. It's called a quadratic span program because you have span vectors. So if you think back to your linear algebra class, then what's a span vector? It's a collection of vectors that give you all the axes. Okay, so if it's three-dimensional, the x-axis, the y-axis, and the z-axis are a spanning set of axes. It doesn't have to be x, y, and z. It could be diagonal things, as long as I can generate any point in the space by some combination of those three axes in three space. So that's why it's called spanning. And you have, it's called quadratic span trees because you have two sets of things that you're worried about. One is you want to model the input to each gate in my Boolean expression. And the other thing is you want to model the output of each gate in my Boolean expression. So I have two separate sets of span programs. And they're two different functions. The input is for the prover, and the output of each gate is for the verification. And please don't ask me any more questions about this. So that's how close I got. Okay. So a Boolean satisfying problem is NP complete, so there's a zero knowledge proof. The key generator creates these tokens, and you can then throw it away. So there's a video of somebody making up, I'll talk about zero cash in a minute, but somebody making up this, publishing the tokens and then running over their computer that knew the secret numbers with a car. Actually, I should have gotten Phil, and it was a crusher. To hark back to the keynote this morning. So The prover asserts that a particular string is true, and the verifier verifies that. But depending on what you choose to encrypt, you can hide every piece of knowledge or just a little bit of piece of knowledge. So again, let me take the case of me transferring money to Kurt. I can have the amount. I can hide the amount by encrypting it. I can hide that it's me that's doing the transfer, and I can hide that Kurt is the recipient. It's my choice. Okay, when I set up the contract, it may be that I want to keep it public, and again, it depends on the context and why you're using the blockchain. Okay, so it may be that it's public, but the amount is private. So it may be some other combination of that. So zero cash is a cryptocurrency where everything is encrypted. And like I said, there's a video somewhere on YouTube that shows somebody driving over the computer that knew the prime numbers. So what's a transaction? Well, it's about what you would expect, a little more than I said before. So what's the from account? That's my account. What's the to account? That's Kurt's account. Again, could be encrypted, doesn't have to be. How much money am I going to transfer? Do I have that amount of money? And do I own the from account? Okay, so I express this as a Boolean expression and run through the steps. So the modules, or the components, I don't know what you'll call it, the functions of Zcash, of zero cash. There's an initial setup stage where you create the public tokens. There is open an account. There is create a new zero cash coin. There's verifying transactions. There's spending coins, and there's receiving coins. Okay, and this begs the issue of the platform that it's on. So there may be fees associated with various steps. It's not in this contract. That's part of the platform. It may be that when I create a new zero cash coin, I need to get it verified by some consensus mechanism. Not part of my contract, part of the platform. Okay. So there are these things that are outside the contract. So zero cash relies on public tokens, relies on immutability. It can keep encrypted all the elements that you choose. Well, zero cash does keep encrypted all these elements. So one of the weaknesses of Bitcoin is that it did not keep encrypted the recipient account, and maybe even the transfer account, I don't remember. It didn't keep encrypted the amount, so that the forensic people could go look at the Bitcoin, at the transactions, and decide how much money was going to be in a particular account and use that as some sort of legal mechanism. So Zcash doesn't have that problem, or virtue. I don't know whether it's a problem or a virtue, depending on your perspective. Okay.
Len, I have a question.
Sure, another question. Oh, no.
At some point you mentioned, at some point you mentioned this idea that there's some data that goes on the blockchain and some data that goes off the blockchain.
Right.
This kind of like makes some noise for me in the sense that there's some properties of the data in the blockchain, and don't you need to ensure the same properties in the data of the blockchain?
Okay.
And just a second. And so in the end, don't you have to replicate kind of all the infrastructure for the data off the blockchain?
No. So the quick answer is no. Okay, so let me give you the example of the audio files. So I have an audio file. I put it out on a public platform. I create a hash of that. Now, I put the hash of that as part of my transaction. And so as long as the hash, as long as the block containing that value doesn't change, I can replicate that block as many times as I want without changing the audio file, without having to transfer the audio file. I just have a link to the audio file and a hash of its value so that I can guarantee that the audio file has not been altered.
But don't you need to replicate the audio file over several nodes?
So what do I have to do in order to make sure that the audio file is available? But that's different than replicating across all the blockchains.
Okay.
And so what people do is they use, people know what IPFS is, Interplanetary File System, perchance? Okay. So this is a file system that you access via hash address. And it takes care of the replication as much as you need to get reliability. So you have to kind of trust the IPFS people. Okay. Okay, so what are some applications of blockchains? So first of all, this is the result of a study done by the World Economic Forum a couple years ago. And they did a study of who was interested in blockchain. This was 3 years ago. And what they found was 80% of the banks are going to have blockchain projects, like DLT, distributed ledger. There are billions of dollars in investment. I believe that Australia has a digital currency produced by the Australian Central Bank. It lives in parallel with the Australian dollar. So central banks are looking at this because you can't counterfeit it. Okay, so from a central bank perspective, electronic currency can't be counterfeit. There are all kinds of blockchain consortia. I was just reading the other day about one having to do with food safety. And I'll get into the supply chain problem in a minute. But there have been a lot of problems in the U.S. in the last year with contaminated lettuce and things like that. So blockchains is proposed as a problem, as a solution rather, to be able to do that, to track it. But if you look at all these uses, the banks are talking about transferring money across banks, across countries and banks. This is a little bit different. Central banks a little bit different. Blockchain consortium. This is transferring things across organizations. The others aren't relevant. So all of the proposed uses of blockchain involve agreements between multiple users and organizations. And so one valid question is why all of a sudden are these users and organizations collaborating when they haven't up to this point? I have a plausible answer. Oops, which I'll get to in a minute. So blockchains is an architectural design choice. The question you ask is why would you use blockchain instead of a distributed database system? Because in some sense it's a distributed database system. And it's very good for integrity and non-repudiation. It's hard to modify the contract because once you have the blockchain, if you're going to modify the contract, how do you validate the things, the transactions you already have that were done under the old contract? It's good for availability. You can make it as confidential as you want. It takes a long time to write, but they're fast reads. And the performance is a problem. And there are proposed solutions for this. So if you look at a blockchain versus, looking too fast, versus a shared database, the database is CRUD. You can delete things, you can update things. Blockchain you can only add, can't ever change. Here you can have master-slave or multi-master, standard database things. On the blockchain you have full replication. Here you have distributed transactions. Okay. There you have to have some sort of consensus mechanism. There are local integrity constraints on a database, but there are global integrity constraints on the blockchain. So Here's essentially a flow chart, and out one end you get an answer that says I need the conventional database. Out the other you get an answer that says I need a blockchain. This is the picture that caused me to be here today because EPEC saw this picture last year. She said you got to come to SATURN and show that picture. She didn't put it quite that way, but that was the gist of it. So, are there multiple parties? No reason for blockchain. Do you have trusted authority? Is it centralized or decentralized? Do you need transparency? Can the data be shared with encryption? Do you need a transaction history? Bunch of questions. Do you need immutability? So you can parse that for your particular proposed use of blockchain. So let me talk about something that, I was in Australia for a couple years, and I had a friend that ran a cotton farm. So he says, I run the cotton farm. And I said, okay, well, that sounds nice. My cotton farm is 90,000 acres. Which is not what I would call a farm. So this is a big deal. And if you ask him, and his company is investigating blockchains. They're working with one of the Australian banks. And you ask him why. And so the first thing to understand is that cotton is transacted in American dollars. And he lives in Australia, and they have Australian dollars. So there are exchange rate fluctuations. So what happens to cotton? Well, you grow it. You harvest it, you get all the seeds out of it. That's what happens at a gin mill, not drinking. You then bale it up. You put it on a train. Train goes to a port. From the port, it goes to a ship. From the ship, it goes to a destination, gets unloaded, gets put on a truck, and turned into cloth. And eventually it ends up in a shirt or a blouse or something like this. And his company tracks it all the way down to here so that he can look at a piece of cloth and tell you how much pesticide was put on the acreage where that plant that went into that was grown. I was taken aback is an understatement. I was stunned by the technological sophistication of cotton growing, at least at the level that his company works. At each one of these steps, now think of having a blockchain. At each one of these steps, I have an authorized user certify that I have harvested, I don't know what the units are before they're baled. I've harvested, so many clumps of cotton. And I can get some money to my friend that owns his cotton farm from the people that picked it. At each step, I can do a transaction of financial transaction, because the normal model is that my friend doesn't get any money until the cloth manufacturer gets it. At which point 6 weeks have gone by and the Australian dollar is now worth more or less than it was before. And it was important to his company to be able to predict it. He didn't really care whether it was more or less, but he wanted it to be predictable. And so he's getting incremental money at each stage of this. And if you know anything about how ports work, incredible number of organizations involved. Okay, so you have trucks coming with all kinds of cargo. They get unloaded. They get distributed to ships. So it's kind of a hub and spoke thing. Trains come in, ships go out. So I have the owners of the train cars. I have the owners of the goods. I have the owners of the ships. At least 3 parties involved in this. Okay. And now back to the question of why didn't these people get together and use a centralized database to manage this? And my answer, and this is not something I've seen anywhere, but at least my answer is there are now platforms that make it cheap enough to do that whereas there didn't used to be platforms. So the blockchain competition among these various platform vendors has resulted in a supply chain blockchain, if you will. And so producing that is cheap enough so that the various parties can sign into it without having to invest as much in entry costs. All they have to do is link to the blockchain and follow the conventions in the blockchain. So I think it's an echo of the fact that blockchains have become popular, that these platforms exist. This is speculation on my part. So right now you have multiple organizations. There's a loss of around 10% of the goods that are shipped into a port. So that's big money in any currency. You have a lack of transparency. You don't know what's going on. There's currency exchange. There's quality control. Somebody dirtied up the cotton, things like that. And so these are problems that will be not necessarily solved, but at least simplified or ameliorated with blockchains. So this is using blockchains in a supply chain. And the same, if you replace cotton with lettuce, you're not actually tagging the lettuce, but you're tagging the containers the lettuce go into, and you know where they come from, and you're tracking those containers until it goes into a distribution center, and then gets put out into the salads or whatever it happens. So again, why now? And my answer is that the overhead has gone down. The overhead of doing these kinds of processing has gone down. The pressures, the competitive pressures have increased. And so you can set up a system whereby the grower gets incremental payments as his cotton goes through each stage, which was hard to do before, and so on. And there are platforms and vendors that will provide solutions at a reasonable price. Again, this is speculation on my part. Okay, this is a student project. So my current affiliation is I'm an adjunct professor, or an adjunct faculty. I'm not even a professor. I'm a faculty at the master's program at Carnegie Mellon. So if you know anything about the academic world, the pecking order of the academic world, you have full professors, you have associate professors, you have assistant professors, you have lead secretaries, you have undersecretaries, you have janitors, and then you have adjuncts. So I am at the very bottom of the food chain. But I got to be a sponsor for a project that they use. And the project was with somebody from Australia. And he is interested in business process models and blockchains. And he said there ought to be a way of translating from a business process model, something written in BPMN, into a blockchain. And lo and behold, there is. And it's the output of this student project. And Hyperledger is the tool that they used. And so actually there are two parts to this. One is to take a visual process model and turn it into BPMN. That was done already. And then the second part was to take the textual BPMN and turn it into calls to Hyperledger, and that's what this student did. So if you're a business and you have business process models, and every business pretty much does, then you can transfer your business to blockchains relatively straightforwardly. Okay. So just a summary. So blockchains are heavily hyped. They're actually toward the bottom of the Gartner hype curve at this point. So if you know the Gartner hype curve, there's a peak of expectations and a trough of disillusionment. So blockchains are somewhere headed toward the trough of disillusionment, and then they come back up to where they're sort of recognized as a tool in your toolbox, but not really silver bullet and not, I don't know, what do you kill vampires with? Not your exploding bullet. The stake, not a wooden stake, whatever the opposite of silver bullet is. And you can think of it as a distributed database with certain properties. There are variants. I went through a number of variants, and you have to choose them. And they're being used, or at least tested, in a variety of domains. And so the people I worked with in Australia wrote a book. I wrote the foreword. I don't know why my name isn't on there. Called Architecture for Blockchain Applications. Usually they have forward by, something like. I'm sorry?
You're slipping.
I'm slipping, yeah. So it was how much time? So it was actually kind of an interesting process. What I said in the foreword is that everybody hypes blockchain as being a terribly disruptive technology, but it's really not. I mean, it disrupts, the people doing databases and the people doing bookkeeping in various industries, but that's no different than other kinds of disruptions that we've had. It doesn't disrupt, it's not like the World Wide Web, it's changed everything. It's not like other disruptive technologies. So I said, cool it. That was my forward, and the response from the Springer people was, that's too negative. So I didn't say cool it, I said learn to live with it. And they were happy. And then just a shameless self-promotion. So this is almost a picture of the cover of my new book. Has nothing to do with blockchains. The interesting thing is my daughter took that picture. So she's now a published photographer. But you can get this for $9.99 on Amazon. Okay, questions?
Thank you. Questions? Yeah.
Or heckling. I mean, people said they were going to heckle me.
Thank you so much. No, thank you. So my question is kind of broadening of the applications. So, I mean, it sounds like you've been doing this for a while. Where do you see this going? Are we going to see like distributed databases that do this, that are just kind of general data, or is this going to be mostly relegated to where you really have a strong, like you need to build trust between multiple organizations and how they interact?
I would say so the question, you had a microphone so people could have heard you, yeah. You don't have to repeat the question. I would say the latter.
Okay.
Centralized or even distributed databases have a real use. You don't always need to have immutable data. You could even keep a log of data changes and get almost the same effect. So I think so if you do a search on uses of blockchain, what you'll find is that the uses that are proposed are multiple organizations, frequently across international boundaries. So one of the things that happens when you move internationally is it's very difficult to enforce a contract. So think of this as a legal contract, even though it's not. You can think of the smart contract as the rules for what's going to happen. And enforcing that internationally gets to be incredibly complicated. If you're an international lawyer, you're a very wealthy person. And so it gets to be incredibly complicated. And so if you look at uses of blockchain, what you'll find is that they tend to cross national boundaries, they tend to cross organizational boundaries, and immutability becomes an important attribute. Yeah.
Yeah, so another question is, for public blockchain network, because everybody can join and leave, and for a new transaction to get consensus, so it should get enough nodes to vote. How we decide in a public network in a worldwide, how we decide
So-
that's enough nodes vote?
So the question is, how do you guarantee that you have enough nodes to?
How we know, the first question, how we know that's enough nodes?
How do you know if you have enough nodes?
Yes.
So I mean, this is an availability question, right? If I have nodes on a network, you know, so I know some cloud data. So on Amazon says that if they have a data center with 64,000 computers, then every day 5 of them will fail. Google announces sort of similar things. So
The question was about how many votes to reach.
how many votes or how many nodes?
How many nodes in the blockchain network? Because you have so many machines, but not every machine in the blockchain network.
Oh, yeah. So the question is, how many nodes do you
Yeah.
need?
So before that,
and so the answer is you do some reliability arithmetic, right? If I have n nodes and they all have a copy of the blockchain and each one of them has a certain probability of failure, then what is the probability that I can access a live node in a reasonable amount of time?
so before that, we don't know n because everybody can join the network.
But you don't necessarily have a node. Just joining the network doesn't get you a node. Joining the network gets you access to the network. Setting up a node is a special thing.
So it's not total free. So if I want to set up a machine to join the network, I have to get some permission from
Right.
somewhere. So that maybe some
There
organization
are
control.
fees associated with joining it, and there are fees associated with having things accepted, and there are rewards for that as well.
So
Yeah.
in other
I
words,
see.
there's a governance structure.
There is a governance structure.
You jump from trust model of consensus, and I think somewhere in there in the Thanks, Kurt. Somewhere in the trust and the consensus is this idea of governance that dictates which protocol it's going to be and what the rewards and so on are, right?
So this is set up by the platform, yes. So the answer is yes, and it's set up by the platform that these are the rules that you have to adhere to in terms of joining and so on. Yeah, question up front.
Are you aware of guidelines or methods to design the blockchain solution in terms of, for example, deciding which contracts need to be established or which data goes on or off the blockchain or like that? Like
I think this is a wonderful problem. It sounds to me like you're proposing a talk for the next Saturn. Well, so there's a little bit of that in that book that I just adhered to. So this has some design principles and so on. I don't know that it would qualify as a method, but this talks a little bit because it's what is the architecture that you need for a blockchain application. So it talks about it somewhat.
The truth, I have a student working on that, and he did research, and he said he didn't find anything. So I was just like,
Ask him to
check.
read the book.
Yeah,
Yeah.
I already took the picture.
Other questions?
I'll just yell, blockchain voting, real or not?
What do you mean? So what do you mean by blockchain voting?
So people are already coming up with systems that they're proposing and will trial for using blockchain to track online voting. Will that succeed or no?
Okay. I thought you meant voting on the blockchain. You mean using blockchain?
Electoral process.
The electoral process. That's part of the problem, or that's part of the solution. It's not the whole solution to electoral problems. But if you have a record, an immutable record of what votes were cast, where the caster is anonymized, then that's a part. It seems to me to be part of a solution. I wouldn't say that's all there is to it. There's a whole access and author. There are a whole bunch of other issues associated with with the electro process, but that would be part of a solution. That would be my opinion.
In your experience, to which degree does an architect of a blockchain-based application have to know all these details of this cryptography that you explained? And where is it made invisible, so to say, by the platform? And what is the necessary degree you have to know? Because otherwise maybe your abstractions break or are leaky and you come up with serious problems in your design.
So how much do you need to know to use blockchains? And the answer is you need to decide on a consensus mechanism. You essentially need to decide on the variance that I talked about. You don't need to, and you need to decide which different blockchains use different encryption models. So quadratic span trees are not used universally; they're just used, in essentially research prototypes at this point. So there are other kinds of theoretical bases. You need to know what you're going to encrypt. You need to know what you're going to put on the chain and what you're going to put off the chain. You need to decide on a consensus mechanism. What else? Private or public, yeah. But the actual internals of the cryptography you don't need to know. It's sort of like using SSH. You don't need to know the Diffie-Hellman algorithm to use SSH. It's just I find that fun.
Sixth sense of fun.
Okay.
Any more questions?
I think that was a good ending. I have a sixth sense of fun. I don't know if that was sick, S-I-C-K, or sixth, S-I-X-T-H.
So the only question I have, did you contribute that BPMN code integration back
So I didn't own it.
to the open source project?
I don't own it. The students owned it, and they did make it open source. I don't know where. Yeah. I mean, as you know, you making something open source doesn't.
The BPMN graph looked exactly like the Red Hat.
So the BPM graph
stuff.
is not part of their solution. The BPMN graphing engine was a modification of an open source BPMN. But the actual translation to hypertext is open source, but I couldn't tell you offhand where it is.
Okay. Yeah. Well, thanks. This was really like. All right. Thank you.